The examples considered so far involve continuous input variables. Variables varied between 0 and 1. In practice, we often have access to a set of input variables that can be continuous or discrete. There are three main types of variables. Continuous variables, for example in a medical context, blood pressure, which can vary continuously, and discrete variables that take only a small number of distinct values and can be of two types. Discrete ordinal variables have a natural order, such as the Glasgow score, to measure a patient's state of consciousness, which varies between 3, deep coma stage, and 15, fully conscious stage. In contrast, nominal or categorical discrete variables simply distinguish different categories and have no natural order, e.g., different types of treatments. Most machine learning algorithms only work for a certain type of input variables. Specific modification may be required to accommodate other types of variables. The great strength of decision trees is that they can handle all three types of variables simultaneously. Whatever the type of variables considered, the decision tree works in the same way. It will look for the split that maximizes the impurity reduction among all possible splits. We just need to specify what is the set of possible cuts for each type of variable. We have already seen the case of continuous variables. The trees seen previously were for continuous input variables. The cuts were all of the form xj less than s, for j a direction among 1d, and s a cut position along this direction j. Such cuts do make sense. The variable being continuous, we can separate the large values from the small ones. The same kind of cuts is considered for ordinal discrete variables, since they are naturally equipped with an order. The nominal variables are different because they do not have a natural order. Therefore, it does not make sense to group the small values together. Let us take a simple example in which we seek to predict the survival time of a patient entering the ER according to the type of treatment he/she receives there. Let us imagine that three types of treatments, arbitrarily named 1, 2, and 3, are available. These treatments are marked with integers, but there is no reason to think that treatment 2 is more effective than treatment 1, or that 3 is more effective than 2. So we cannot use this order as a natural order on the treatments. Perhaps treatments 1 and 3 are the most similar, but such a separation, 1 and 3 on one side, 2 on the other, is not allowed by the order on the integers. It is therefore necessary to encode such variables. Under scikit-learn, all input variables of a tree are considered as continuous. It is therefore absolutely necessary not to encode a nominal variable in the form of an integer, because it will be interpreted as being naturally provided with an order. To deal with this type of variables, we should consider all possible separation of modalities. Specifically, if we denote by big C the set of modalities that can be taken by the variable in question, all cuts of the form C versus C complementary should be considered, where C is any subset of modalities of big C. In other words, all cuts that separate the set of modalities into two distinct groups are admissible. However, finding the optimal cut among all these cuts is often computationally impossible, especially for variables with a large number of modalities. One-hot encoding is a commonly used substitution technique. It consists in separating the nominal variable into as many 0-1 binary subvariables as there are modalities in the initial variable. The subvariables thus created are called dummy variables. A modality of the initial variable then corresponds to all the dummy variables equal to 0, except the one coding for the modality in question, which is equal to 1. In our example, the initial variable type of treatment, which can take three different modalities, would be split into three new binary variables. The first one coding for the surgical treatment, the second for drug treatment, and the third for no treatment. A value of 100 for this set of three variables then corresponds to surgical treatment. The name one-hot comes from the fact that only one of the components is equal to 1, the other equal to 0, the component in question corresponding to the modality taken by the variable. Using the one-hot encoding for a nominal variable within a tree leads to consider cuts of the type one modality of the initial variable against the rest of the modalities. Indeed, the tree can cut according to one of the dummy variables, each corresponding to a modality of the initial variable. This is a way to avoid the computational cost of the exhaustive search for the best cut. One-hot encoding is therefore computationally attractive, but can reduce the predictivity of the model. If the best split was of the form one half of the modalities versus the other half, it will be difficult to construct it with one-hot encoding. The tree will then be suboptimal. Nevertheless, one-hot encoding is the most widely used technique for encoding categorical variables for decision trees or for other machine learning methods. Using a one-hot encoding for nominal variables is therefore not a panacea. Fortunately, in a binary classification framework, there is something better to do: target encoding. To illustrate this alternative method, let's choose a cutoff criterion, for example, the error rate. Let us then consider a nominal variable xj that can potentially take a large number of modalities. We will reorder the modalities of this variable so that the frequency of occurrence of observations with a label y equal 1 among observations with the first modality, xj equal c1, is the smallest. In other words, c1 is the modality for which we make the most error in predicting y equal to 1. The c2 modality is the second modality for which we make the most errors in predicting y equal to 1, and so on. We have thus reordered the modalities so as to have c1, c2 until cl. We can then only consider cuts of the form xj in c1 until c small l versus xj in cl plus 1 until c big L. The set of these cuts is of size L minus 1. It can be shown that the cutoff maximizing the impurity reduction for any of the above criteria is a split of the form of equation 7. Using this trick of reordering the modalities according to the frequency of appearance of the output variable, we can therefore find the optimal split by comparing L-1 splits. The aforementioned one-hot encoding method compares L splits of the form one modality against all the modalities, but with no guarantee that the best cut is in this set. Conversely, an exhaustive search for the best cut leads to comparing 2 power L-1, which is computationally impossible in general. This trick works in the context of binary classification and regression. It is then sufficient to replace the proportion in equation 6 by the empirical means. However, this trick is no longer valid in the case of multi-class classification and cannot be extended to this framework. It is then necessary to resort to the one-hot encoding described above. In summary, decision trees are supposed to naturally take into account nominal variables, which is not implemented in scikit-learn. Therefore, one-hot encoding must be used in general, a procedure that is efficient in terms of computational time, but without guaranteeing statistical optimality. In the case of binary classification and regression, target encoding makes it possible to find the optimal split by evaluating a reasonable number of splits equal to the number of terms of the nominal variables in question.